Thousands of kilometers of massive steel oil pipelines lie silently along the seabed of Saudi Arabia, hidden beneath the weight of the Persian Gulf. This vast underwater infrastructure serves as a critical artery for the global economy, moving the energy required to power entire nations. But why was it necessary to place thousands of kilometers of steel pipelines beneath these desert seas? At first glance, the task of laying heavy metal on the unstable ocean floor seems impossible. Yet without this submerged network, the continuous and safe transport of crude oil from remote offshore fields to mainland processing facilities would be unachievable. The answer lies deep beneath the ocean floor, where the flow of energy begins its journey. Saudi Arabia has expanded its offshore pipeline network since the earliest stages of the Middle East's oil industry. These systems were designed to ensure that raw resources reach international markets without interruption. One can notice how the thick-walled steel pipes are treated to withstand the corrosive salinity of the deep. But this is just the beginning. Engineers encountered enormous technical hurdles when first installing these heavy conduits under the water. The equipment gradually lowers the segments using massive tensioners that prevent the steel from buckling under its own weight. It is visible how the pipe reaches the seabed, settling into the silt with calculated precision. The process is only gaining momentum as the network grows to cover the immense distances between the drilling platforms and the shore. Every kilometer of the pipeline is a testament to complex logistics and specialized maritime construction. Therefore, the steel must maintain its structural integrity under extreme pressure for decades. It only looks obvious to lay a line in a straight path, but in reality, the seafloor topography requires constant adjustments to the trajectory. The material is ready to move to the next processing phase without haste. $100,000 or more per year represents the starting point for compensation in the world of high-stakes extraction. Why do companies pay such significant sums to those working in the fields? The answer lies in the extreme conditions and the immense responsibility of maintaining a resource that serves as the lifeblood of the global economy. One can notice how hydraulic systems heave and massive drills bite into the earth to secure a supply that powers everything from container ships to the electricity grids of entire cities. But this is just the beginning. The familiar slogan of "Drill baby drill" has returned to the forefront of the economic conversation as a means to stabilize the national market. In reality, oil has functioned as the primary driver of modern civilization for several decades. It does not only serve as fuel for airplanes and automobiles. Thousands of industrial sectors, including chemical production and plastics manufacturing, depend entirely on this liquid resource. Everything only gets more complicated when the supply chain is interrupted. A small fluctuation in the price per barrel can trigger a massive chain reaction across the globe. Transportation costs surge immediately, and the price of everyday goods follows. Inflation rises as a direct consequence, and the daily lives of millions of families are affected by these shifting numbers. It only looks obvious to extract oil, but in reality, the process requires constant, exhausting labor to prevent a total economic stall. Workers endure shifts lasting 12 to 13 hours in environments defined by loud machinery and demanding physical tasks. One can notice the camera glides along the massive steel structures of offshore rigs, where men and women spend weeks away from their families. The equipment gradually wears down under the pressure of continuous operation, requiring constant vigilance. It gets more complex further on. Constant risks from explosions or fatal accidents are a permanent reality for those stationed deep underground or on platforms in the open ocean. Safety protocols are calculated with jewelry-like precision, yet the danger of the high-pressure environment never fully disappears. Huge drill bits rotate ceaselessly, cutting through rock layers while monitors track every pound of pressure in the wellbore. The process is only gaining momentum as global demand continues to climb. Therefore, the high salaries reflect the physical and mental toll of such hazardous work. Families remain separated for long stretches of time while the workers ensure the flow of energy never stops. The oil and gas industry remains a world of high rewards and equally high risks, where every hour of labor translates into the stability of the modern world. The material flows through the pipelines, transitioning into the global supply chain without haste. 200,000 steel oil pipeline sections. This is the massive volume of material required to lay the groundwork for the entire offshore project. Each individual unit must be manufactured under extremely strict accuracy and quality requirements to prevent any failure under the weight of the ocean. Why is such a high volume of identical segments necessary? The scale of the task demands a major logistical operation and continuous industrial production capacity. Without this volume of standardized parts, the installation of the offshore network would be impossible to maintain at a steady pace. Action is initiated at 3 major pipe manufacturing plants mobilized across the territory of Saudi Arabia. These facilities operate around the clock, maintaining an average production rate of nearly 100 oil pipeline sections every single day. One can notice how the equipment gradually shapes the raw material into finished components. High-strength steel plates serve as the foundation, specifically engineered to withstand extreme operating pressure and the harsh chemical environment of the sea. But this is just the beginning. It only looks obvious to turn a flat sheet into a cylinder, but in reality, the process requires immense mechanical force. Flat steel plates are rolled into cylindrical forms before longitudinal welding is executed along the seam to create a sealed unit. Each section measures roughly 1,150 millimeters in outer diameter. The camera glides along the metal as lengths of up to 12 meters are reached. To ensure the dimensions are exact, hydraulic expansion is carried out, forcing the steel into a state of perfect roundness. Everything only gets more complicated as the ends of the pipes are beveled. This preparation is essential for the offshore welding that will occur later during the installation phase at sea. The process is only gaining momentum. Every pipe segment undergoes a comprehensive quality inspection process, where non-destructive testing of the weld seams guarantees structural reliability. It is visible how sensors and scanners move over the joints to detect even the smallest microscopic imperfection before the units are approved for deployment. Why is the application of protective coatings considered a decisive factor for the pipeline's lifespan? Raw steel would quickly succumb to the aggressive seawater environment if left exposed. Multiple protective layers are added to improve flow performance and preserve the strength of the metal over time. A low-friction epoxy lining is applied to the inner surface of each pipe section. This significantly reduces resistance as the crude oil moves through the system, minimizing pressure losses along the extremely long offshore routes. Specialized external polymer or epoxy anti-corrosion coatings are simultaneously applied to the outer steel surface. This layer acts as the primary defense against electrochemical reactions and chemical corrosion. One can notice how the coating creates a uniform barrier against the salt water of the offshore oil fields. The material leaves the coating station and transitions into a reinforcement phase. This is where concrete weight coating is completed to ensure the pipe remains stable on the seabed. The process of moving these massive components requires close coordination between manufacturing plants, storage yards, and port facilities. Each pipe section, weighing several tens of tons, is loaded onto specialized transport vehicles or barges. Heavy cranes and handling systems are used to load and unload the material with jewelry-like precision. It is visible how the cranes position the pipe safely to minimize impact and reduce the risk of any structural damage. Transition to the next level occurs at the coastal transfer terminals. At the ports, the sections are stored in large yards and arranged according to the planned installation sequence. This organization ensures that the supply vessels receive the correct parts in the exact order they are needed at sea. Coordinated schedules guarantee a steady and uninterrupted supply of materials for the offshore installation. From these facilities, the pipe sections are transferred onto specialized pipe-laying vessels where the final assembly begins. The material is ready to move to the next processing phase without haste. 24 tons is the approximate weight of a single section of oil pipeline positioned on the deck of a specialized vessel. These massive ships operating offshore Saudi Arabia serve as floating industrial assembly lines, where every stage of installation occurs within a closed-loop system in the open sea. Why is such a centralized deck layout necessary for the construction process? At first glance, the maritime environment seems too unstable for high-precision manufacturing. But without this continuous shipboard assembly, the integration of heavy segments would be impossible under the influence of unpredictable currents and wind. Automated welding systems execute a full circular weld around the joint once the two segments are aligned with millimeter precision. The process is only gaining momentum. Inspection equipment immediately scans the finished connection using sensors to detect any internal defects or potential leaks. Only joints that strictly satisfy the technical standards are permitted to advance further along the deck conveyor. One can notice how the equipment gradually applies a dedicated protection system to the approved connection. This stage involves the application of heat shrink sleeves integrated with flexible filler materials. Such a combination serves a dual purpose, shielding the metal from corrosive salt water while providing the elasticity needed for the pipeline to adjust to the uneven contours of the seabed terrain. The vessel moves forward along a predetermined route at a steady pace. It is visible how the connected segments are guided into the water and lowered toward the seafloor through the synchronized action of transport and positioning systems. Everything only gets more complicated as the depth increases. 3 kilometers of offshore oil pipeline can be installed in a single day using this methodology. Such a speed is rarely achieved in the field of offshore construction. Therefore, the coordination between the maritime crew and the automated deck systems must remain absolute to maintain this output. But this is not the limit of the project's complexity. Geological and environmental obstacles required the engineering teams to perform extensive seabed preparation and manage multiple infrastructure crossing points. In many sectors, the seafloor remains stable enough to support the weight of the pipe with very little external intervention. This was not true for the entire alignment. Specialized support vessels operated ahead of the main laying ship in areas where the terrain was rocky or characterized by significant depressions. The camera glides along the seabed as these ships discharge rock and gravel to fill the voids. This action creates a level and stable foundation for the incoming pipeline. High energy zones in shallow water presented a different challenge due to powerful waves and currents. Because the pipeline could not remain stable if left exposed on the surface, it was placed inside pre-excavated trenches. These seafloor channels were later backfilled with material to secure the pipe and shield it from the constant movement of the water. Transition to the next level involves navigating the existing underwater network. The pipeline route frequently intersected with pre-existing subsea infrastructure such as communication cables and power lines. At every crossing point, workers constructed protective rock berms to separate and shield the various systems from one another. These measures ensured the long-term structural reliability of the entire underwater grid. The material is ready to move to the next processing phase without haste. Millions of years of geological evolution have preserved vast reserves of oil and natural gas within ancient sediment layers deep beneath the Earth's crust. Why are these energy resources, which have fundamentally shaped modern civilization, so difficult to access? Surface deposits are largely exhausted, leaving the most significant fields hidden thousands of meters below the ocean floor, far from any human settlement. To bridge this gap, humanity has engineered massive machines known as offshore oil rigs. The birth of an industrial city in the middle of the ocean begins on land within specialized shipyards. Gigantic steel structures weighing tens of thousands of tons are manufactured with precision before being loaded onto specialized heavy lift vessels for transport. Once the equipment reaches the designated extraction site, fixed platforms are lowered into position with deliberate speed. Enormous steel legs are driven deep into the seabed and reinforced with concrete, providing the stability required to operate in water depths ranging from 60 to 120 meters. Engineers rely on semi-submersible drilling rigs when the mission moves to more remote offshore regions where the ocean floor drops several thousand meters. These structures maintain their balance through massive floating pontoons positioned strategically beneath the water surface. Anchoring systems made of heavy chains stretch for thousands of meters, allowing for safe operations at depths of up to 12,000 feet. It is visible how this distance equals roughly 12 times the height of the Eiffel Tower. It only looks obvious to manage the flow from the surface, but in reality, the critical work happens at the bottom. Just above the seabed, a specialized system known as a subsea wellhead is installed to function as a giant valve. This equipment controls the flow of oil and natural gas while positioned only a few meters above the ocean floor. The process is only gaining momentum as the hardware must withstand pressures hundreds of times greater than those experienced on land. Installation requires near-perfect precision with tolerances measured in mere inches. Because of the extreme depth, the work is carried out using remotely operated vehicles, or ROVs, navigating the complete darkness of the deep ocean. One can notice how robotic arms carefully maneuver multi-ton steel components to connect and seal the pipeline system. Everything only gets more complicated as the oil and natural gas begin to flow from the wellhead into a vast network of subsea pipelines. These pipelines stretch for dozens of kilometers across the seabed in an interconnected grid. Every welded section is protected by multiple anti-corrosion layers to ensure longevity in the harsh saltwater environment. Automated sensors monitor the lines continuously to prevent leaks, as even a small crack could trigger a serious environmental disaster. Transition to the next level occurs at the surface, where floating production, storage, and offloading vessels, known as FPSOs, wait. At first glance, these floating fortresses look like standard ships, but they are not permanently attached to the seabed like fixed platforms. Instead, massive steel mooring chains hold them in position, allowing the vessel to move with ocean swells while maintaining stable connections to the extraction systems below. A single FPSO can store up to 2 million barrels of oil at one time. The vessel serves as an initial processing facility for crude oil and acts as a floating storage unit before the resource is transferred to long-distance tanker ships. One can notice the seamless transition of energy from the reservoir to the hull. From fixed platforms and semi-submersible rigs to the subsea wellheads and vast underwater pipeline networks, every element forms a continuous extraction chain. This system stretches from deep beneath the earth to the ocean surface, transforming energy buried for millions of years into the fuel that powers the modern world. The material reaches the surface, completing its journey from the depths. $100 million. This is the potential cost of a single decision made in the silence of offshore exploration. High-precision survey vessels serve as the starting point for the entire extraction cycle. On the open deck, engineers deploy massive acoustic transmitters that are lowered deep into the water column. Why must these sound waves travel through miles of seawater and rock? At first glance, the ocean floor is an impenetrable barrier, but in reality, the reflected signals captured by surface sensors allow scientists to visualize the invisible. The resulting three-dimensional seismic map reveals ancient sedimentary layers where oil and gas have been trapped for millions of years. Yet even the most detailed digital model cannot offer absolute certainty. The process is only gaining momentum. A massive drilling platform is towed into position at the coordinates identified by the seismic data. Success depends on the assembly of hundreds of steel pipes, each measuring exactly 9 meters in length, which are linked together to form a continuous column. This steel assembly cuts through the ocean water and enters the crust, driven by a drill bit equipped with cutters made of a super hard alloy. One can notice how the entire string rotates ceaselessly to grind through dense underground formations. It gets more complex further on. Engineers wait until the drill reaches the target depth before deploying a specialized monitoring device. This logging instrument contains several integrated sensing systems designed to operate in total darkness. Deep beneath the seabed, the tool releases a combination of gamma radiation, sound waves, and electrical signals into the surrounding rock. The returning signals are transmitted back to the surface as dense streams of data, providing the only window into the reservoir's porosity, pressure, and fluid flow capacity. $50 to $100 million hangs in the balance during these measurements. The data determines if the site becomes a productive field or a dry well that must be permanently abandoned. Transition to the next level. But such industrial power comes at a price in the form of extreme geological pressure. If drilling operations are poorly managed or technical oversight fails, the reservoir pressure can suddenly surge upward with uncontrollable force. This triggers a blowout where crude oil escapes directly from the seabed into the open ocean. One can notice the immediate threat such a failure poses to the marine ecosystem. Environmental disasters of this scale require billions of dollars for containment and remediation. It only looks obvious that the pressure must be contained, but in reality, the mechanical integrity of the well is a constant struggle against the earth. Therefore, every stage of the drilling process undergoes strict millisecond by millisecond control. The equipment moves with calculated precision because the margin for error is non-existent. Even the smallest technical mistake can transform a high-budget energy project into a global environmental catastrophe. The sensors must remain active and the crew alert at every moment of the operation. Thus, the preliminary phase of the well's life concludes, leaving the steel structure ready for the next stage of production. 20,000 barrels per day is the maximum capacity that high-performance electric submersible pumps can reach when natural reservoir energy begins to fade. Once the well is fully secured, the extraction phase commences. At first, the natural underground pressure is sufficient to push the oil and gas upward through the specialized production tubing. Why does this process eventually require artificial intervention? The initial pressure within the reservoir inevitably declines over time as the resources are depleted. Therefore, mechanical systems like gas lift injection or powerful submersible pumps are integrated to maintain a stable and continuous flow to the surface. One can notice how what emerges from the wellhead is not pure fuel, but a complex mixture of crude oil, gas, water, and fine sand. It only looks obvious to call this material oil, but in reality, it must undergo immediate refinement. The process is only gaining momentum. This raw stream enters multi-stage separators, where the various phases are isolated by density and physical properties. Gas is diverted to be compressed for export, or is re-injected deep into the reservoir to help sustain the necessary internal pressure. Simultaneously, the water undergoes intensive treatment to remove oil residues and solid particles. It is visible how the treated water is finally discharged back into the sea, adhering strictly to environmental regulations that govern every liter. The crude oil, meanwhile, moves into additional processing units to eliminate salts and remaining impurities. At first glance, this sequence of separation seems simple, but in reality, thousands of sensors must continuously monitor pressure, temperature, and flow rates at every microstage. It gets more complex further on. Modern offshore platforms transmit this massive volume of real-time data via satellite to onshore control centers. This allows for immediate remote intervention the moment any irregularity is detected by the system. Automated safety protocols can trigger alarms or even shut down the entire well if a sudden pressure drop or abnormal flow condition is recorded. The equipment gradually manages the tightly connected chain from flow control to final phase separation and treatment. Extreme precision is mandatory because even a minor error can result in financial losses worth millions of dollars and cause irreparable damage to the marine ecosystem. After the crude oil is treated and placed into temporary storage tanks, the transportation phase begins. In fields located closer to the shoreline, subsea pipelines stretching for dozens of kilometers carry the liquid directly to refineries. The camera glides along these steel arteries that rest on the seabed. This is not the limit of the logistics network. In deeper offshore fields located much farther from the coast, the crude oil is transferred onto specialized tanker ships or floating storage units. Each of these vessels is capable of transporting millions of barrels across the open ocean. From these massive hulls, the energy resource formed over millions of years begins its final journey toward refineries. The molten gold-colored crude eventually transitions into the products that fuel everyday human life. This concludes the primary stage of extraction and logistics for the offshore energy industry. The material is ready to move to the next processing phase without haste.